With mathematical structures, it's always possible that a clever mathematician will find a way around. Therefore, many codes were broken in the past. Many ciphers were essentially broken because there was a clever guy who managed to break it. With quantum physics, it's different. You cannot break the laws of physics. They are as they are.
Exactly.
So therefore, security based on the laws of physics is much, much stronger.
Let's introduce you to the audience, Professor Artur Ekert. Who are you and how would you describe yourself in one sentence?
In one sentence, I guess I'm a crypto-quantum physicist.
Wow. That's really interesting. I want to know more about how do you have quantum cryptography? Like, what is that?
A quantum part is just about using photons, atoms, quantum properties of them to encode messages in such a way that, say, only you and I can read them, and any third party, as this person who's filming us, for example, cannot really listen to this conversation. So that's the essence of making information secure. Only those who are entitled to this information have access to this information.
And how do quantum technologies really impact the way that we can safeguard and communicate through quantum mechanics?
Well, we can design systems that allow us to guarantee privacy these days. And this privacy is guaranteed not only by sophisticated mathematics, as it is more common, I would say, but the new way, or a quantum way, is to use quantum phenomena. The difference is quite important here. With mathematical structures, it's always possible that a clever mathematician will find a way around. Therefore, many codes were broken in the past. Many ciphers were essentially broken because there was a clever guy who managed to break it. With quantum physics, it's different. You cannot break the laws of physics. They are as they are.
Exactly.
So therefore, security based on the laws of physics is much, much stronger.
Quantum cryptography can give us a different perspective of different fields like physics and mathematics. So what type of perspectives can it give us?
Well, for example, let me give you one example here. In the foundations of quantum physics, people were thinking, where is this randomness coming from? The people were testing the so-called Bell inequalities, trying to understand the nature of physical reality. And that was a very fundamental research in foundations of physics, almost philosophy, and most serious physicists at that time didn't even think seriously about this kind of research. And then at the same time, people in cryptography were interested in generating and shared randomness so that nobody can predict what it is. And unpredictability is important here because if your enemy can predict what kind of codes you use or what kind of encryption you use, that person can break. So now you can actually bring those two fields together.
And how do you go about achieving this? What are you working on to achieve that we can safeguard our information?
Well, that requires a little bit of further understanding of security criteria, some theoretical work, and technology development, especially on the detection side, good photo detectors, maybe better optical fibers. But technology essentially is there. It's just pushing it a little bit further in terms of precision, in terms of efficiency. I think it's almost becoming kind of engineering. And the most fascinating part is that when you reach a certain technological level here, you can design something that is called device-independent quantum cryptography, which essentially says that once you have this technology, you can sell those devices to people that may not even trust you because they will be able to run those devices and devices self-certified themselves. So maybe let me put it this way. Imagine that your enemy has technology and is selling these quantum crypto devices, but you don't trust those people. Would you buy it from them? Today, the answer would be obviously not, because if I don't trust them, they can plant all kind of strange devices into those devices you wouldn't even know, right? Now, with the device-independent quantum crypto, you can buy them because you can test whether the devices do what they do without even opening those devices by running this Bell test, which is a kind of a statistics. I know that maybe it's just a little bit too complicated to explain in simple terms, but essentially the new chapter in quantum crypto is about device-independent cryptography, where you don't even have to trust devices that you have in order to guarantee security of your communication.
Well, that's very interesting, and I thank you very much for your insights on quantum cryptography, and we hope to see it in the future.
Well, pleasure. Thank you for having me.